The Physics of a Small Gas Engine by Andy Granath, Donovan Reed, and Henry Thomas. Engines are found everywhere in everyday life. For as long as written history has existed, people have had a need to convert potential energy into mechanical energy. From windmills turning wet stones to grind grain, to steam engine driving a massive ship, people have developed many different methods to convert potential energy into useful mechanical energy. In our specific situation, we had access to a small internal combustion engine. Internal combustion engines convert the chemical energy of a fuel into mechanical energy that can be used for a variety of uses. The largest issue with these internal combustion engines is the large inefficiency of the engine. Internal combustion engines are very loud and they create a lot of unused heat. This energy is some of the potential energy that is not able to be converted into useful mechanical energy. This results in a horrible efficiency for small gas engines. This leads to the goal of this project, to determine what is the efficiency of a small gas engine.
Before we detail our experiment, we need to go through our theory. So one method to determine the efficiency of a small gas engine is to determine the change in energy of an object connected to the engine. Specifically, you can look at the change in rotational kinetic energy of a spinning mass that is attached to the output of the engine. This is called a dynamometer. A dynamometer is a tool that measures the RPM of a spinning mass with a calculated moment of inertia. This change in energy can then be compared to the maximum amount of energy that the spent fuel contained. Since the fuel we are burning is gasohol, a 90-10 mix of gasoline and ethanol, we know that 1 kilogram of gasohol will release 43.54 megajoules of energy. This information allows us to take the change in energy and the mass of fuel burned to calculate the efficiency of the engine. So our theoretical change in energy will be determined from that gasohol conversion, and the experimental change in energy will be determined from the dynamometer.
Our experimental setup depended largely upon the dynamometer. A photo of the dynamometer that we made can be seen on the right. Our dynamometer consisted of a concrete spinning mass mounted on two pillow block bearings connected to the engine output with a 1-to-1 gear ratio. The concrete cylinder had a strong hard drive magnet embedded in it that would trip a Hall effect sensor on every revolution. This Hall effect sensor is the key to the function of the dynamometer. A Hall effect sensor detects the presence of a magnetic field, and due to the fact that a magnet is mounted on the spinning mass, the Hall effect sensor allows us to measure the RPM of the spinning mass. The sensor, combined with a program called Simple Dyno, pictured to the left, allows us to gather information about the initial and final angular velocities. This, combined with an electronic balance, allows us to collect all of the data we need to determine the efficiency.
Shown here is a video of the engine running. There were a few assumptions that we made during the experiment. These were made both due to the constraints of our setup and the constraints of our measurement devices. One major assumption that we had to make was related to the calculation of the moment of inertia. When we created the mass for the dynamometer, we filled a coffee tin with concrete. This causes some issues in the moment of inertia calculation because concrete is not a uniform density. Since our calculation for the moment of inertia assumes that the cylinder is a perfect uniform cylinder, in which category the concrete tube does not alas qualify. Another assumption that was made for the experiment was that there was no loss of energy to friction. This is obviously not possible because there will be energy lost due to friction in the gearing of the engine and the bearing surfaces. The last major assumption that we made was that the fuel usage was constant throughout the duration of the test. This is not really the case because the engine will use more fuel when spinning up from idle, but we only calculate the fuel usage based on idle timing.
Our procedure for gathering the data was very simple. The process consisted of two major parts. The first part was to determine the fuel usage of the engine. To do this, we first masked the fuel container that was full of fuel. This container was then reattached to the engine, and the engine was then run for a known amount of time as determined by the stopwatch. The engine and stopwatch were then stopped, the tank weighed, and all the data was recorded. This gives us the fuel usage versus time data. The next part was to determine the change in energy of our dynamometer. Since the mechanical energy converted by the engine is used to spin the dynamometer weight, the mechanical energy converted by the engine is turned into rotational kinetic energy, and we can use the initial and final angular velocities to calculate the change in rotational kinetic energy, and therefore we can determine the mechanical energy converted by the engine.
This is the data that we collected for use in the analysis part of this lab. Before we go into the analysis, we need to acknowledge one major thing. As you can see on our previous data slide, we only had one data point for our experiment. This was not the original plan. We had planned to do at least 3 trials and were going to average the efficiency, but the dynamometer had a catastrophic failure. Bolts went everywhere. The mass could not take the forces created while it was spinning, and it was destroyed during the second run. We may have been able to salvage it and complete more runs, but the destruction of the mass took the Hall effect sensor with it, and there was no way we could source a new one in a reasonable time frame. To determine the efficiency of the engine, we first had to determine the change in rotational energy. This change in rotational energy is the energy output of the engine. We used the equation K equals IW squared, which is the equation for rotational kinetic energy. Using the curve for angular velocity over time, we used the initial and final angular velocities to be able to determine the initial and final rotational kinetic energies in the run. The difference of energies was found to be 2,126 joules of energy over 6.2 seconds. We then had to determine the amount of fuel used in a run. We used a dry run with the same load and setup as a real run and determined the fuel usage per second based off the initial and final mass of fuel over a period of time. This fuel usage was determined to be 0.0825 grams per second, and to determine the theoretical potential energy of the gasoline used in the run, we used the energy density of gasoline, which is 43.54 megajoules per kilogram, and found that there was a theoretical potential energy of 22,282.15 joules, and using the measured mechanical output and theoretical potential input, we calculated that the engine was 9.54% efficient.
Based on the data collected and the calculations done, we found the efficiency of the engine to be 9.54%, which makes sense given that the most efficient engine created is 38% efficient. And this loss in energy makes sense because the engine gives off heat and sound kinetic energy while it's running. Our engine was also vibrating a lot during the trials, which is another loss of kinetic energy. Friction also does work against the spinning of the mass, and thus causes the change in rotational kinetic energy to be less than what it would be without friction. To improve further experiments, it would be best to get a more stable dynamometer, because with a more stable dynamometer, more trials will be able to be run, and more trials means a more accurate value for efficiency.